Hello and welcome to my today's video, which will be about unboxing of our new product ACR-EX, which is a to be ATEX certified pulse to narrowband IoT converter with display to show the counter value. So I'm already showing you the graphical user interface, which we will use for configuration of the device. But before we dive deeper in this, I will do the actual unboxing. So here's the device. It comes in such a paper box. You can see on the box the name of the device and serial number, which can be also read from this QR code. I will open the box. Here you can see already the IMEI of the device, and in case the device is shipped with a SIM card, there's also IMSI and SSID, which are numbers related to the SIM card. Inside you can see the actual device, which is wrapped in a ecology friendly protection from paper, and here's the actual device. This is the front part. It contains the IEC 62056-21 interface for configuration, address of our company, name of the device, display for showing the counter value, logo, and on the other side there is a sticker which contain, let it zoom, which contain all information about the device, the firmware version, hardware version, IMEI, serial number, etc. And there is also the ATEX code here to reading the information out of it. So let's get inside. Oh yeah, I was lucky. Normally this thing gets by itself screwed, so I have prepared also a screwdriver here, but I was lucky this time. Inside we have a battery. It's a C-size primary lithium battery. Here is a place where we put the SIM card. Here is the connector for the battery, internal narrowband IoT antenna on the PCB, serial number with the data matrix code again, the display, LIC supercapacitors, which helps the battery, especially in freezing environment. And here is a red read switch, which is used for activation of the IEC interface, and in signal tester mode it can be also used to trigger the message manually, to trigger the signal testing message manually. Okay, yeah, and I also forgot the quite important part of it because it's a pulse to narrowband IoT converter. So where you connect the wire where the pulses are generated, it is here to the bugle connector, which is very user friendly. You just pass the wire through this gland. You tighten it so that it's IP67 protected. I forgot to show this insulation, which is a single piece. It is not inserted, but it is prepared like this in the fab. And yeah, and here you insert the wires. There is a ground on the left, on the right there is a positive, but if you use a dry contact, you don't care about the polarity. It can also work with a non-dry contact, up to 24 volt. Okay, I will not insert any wire there for now because it's not important for the demonstration. But I guess we should insert the SIM card, so let's do it. Yeah, I'm inserting the SIM card in a demo mode, so it took me more time than normally. I connect the battery, and the device starts blinking like this. It blinks with the initial speed, and then the speed changes to a little bit slower. what it means. When the device starts, it runs so-called bootloader, which is used for firmware update. The firmware update can be done either via NB-IoT, or it can be done via this IEC 62056-21 interface. The initial blinking means that it is trying to detect whether there is a new firmware being pumped in using this interface, and when the speed changes, it starts to connect to NB-IoT to receive a new firmware. We can wait, it would boot by itself, or if we don't want to wait, we can hold the head or any other magnet close to the read switch, and it will skip the bootloader like this. So now the device is booting. You can see starting on the display release 112, which is the version we could see also on the sticker. Now it is detecting the SIM card, and okay, now it is connecting to the network. Sometimes it can take some more time, yeah, and signal 19, and it is sending the first payload right after connection. You can see the progress of sending on the display, so you can see that something is actually happening. Yeah, like this. So let's wait until the device sends its first payload. I think there is nobody answering the device currently. There is no backend running on the other side, so it waited for the full timeout. Normally it's faster because it sends the frame, and right after sending it, it will receive any answer and acknowledge, for example. If it doesn't, it will wait for the full timeout. So we could see counter, date, time, and now back the counter, which is 0, obviously initially. The power consumption of the device is on average approximately under 30 microamp, let's say, which makes it last up to 10 years with no issues. And yeah, we have the device ready, we have the head ready, so let's deep dive in the configuration of it. So I will approach the head like this, and I have the IEC ready, and I can put the head where it should be. Now in the GUI, I click on connect, I select my head, and when the IEC is still shown, I can click at load config from device. You can see on the display that it goes through the programming mode, and it reads all information from the device. You can see the values, so I will now explain one by one what the values mean. So this first mode is actually value of this combo box, which reflects in which mode the device is working. The main purpose is that it is a pulse counter, and it sends the data over UDP. Why we put here UDP is because we plan to have also a lightweight machine-to-machine LWM2M version of the firmware, or the mode. The device can be configured in the mode, so the firmware is common. And we also have a signal tester mode, where it reports the signal it detects over UDP. So it's an alternative mode which was requested by our customers. Here the information about the device is loaded, but it was not loaded this time. Let's check with the other mode. Here is the identification. This is sent at the beginning of every frame which is transmitted. I can put there, for example, my underscore device if I want. Here is the pulse counting setting. So this means that 1000 to 1 means that there is 1000 pulse to form 1 cubic meter, which defines where the decimal point on the display should be shown. Here is the sampling period in seconds. I can put there anything I want, for example 3600 for 1 hour. Here I put the unit of what will be reported, and obis code of what will be reported. This is then used when I read out the archive of the device, because the archive is sent every day to the remote server using UDP, or it can be also read out using the IEC interface through this section. Read archive, we will see it later. This is also interesting. This is what should be the period of detection of the maximum flow through the device and minimum flow through the device. With 300 it is set to 300 seconds, which is 5 minutes. In section 4 we have settings of for timing of sending. So we say that every day at 6 o'clock in the morning it should send the hourly data, in this case, to the remote server. And if I put here 00 to the spread, it means that all devices will send the data at the same time, which is not good for distributing the load to your server. So I recommend you to put here, for example, 1 hour, which will make it send data from 6 to 7 o'clock. If you need to have less, you can put here 0 and here, for example, 10 to have a 10-minute spread. Here is the IP address to which the data will be sent, and this is the UDP port to which it will be sent. We use Miotic SIM card, so this is IPN port for Miotic service, where we then configure where the data should be further forwarded. Here we go to the narrowband IoT settings. So first is the APN. With auto, the APN is taken from the SIM card. You can put there directly the value of the APN. For example, for Vodafone it would be Vodafone Easy Connect. In Czech Republic it would be this value, but I can put there auto so that I let the device detect the APN from the SIM card. This is things of the PLMN ID. What happened to us, for example, once we had an installation in Božidar, which is close to German border, and the device got connected to German network, even if we wanted it to connect to Czech network. So you can hear, for example, like this, force the Czech network. If you put there 0, the network is automatically detected. And last but not least is the display settings, which is important because it defines the UX, user experience. Here you define how many seconds the counter value should be shown and how many seconds the time and date should be shown on the display. So it is 20 seconds to 6 seconds currently. Okay, so let's imagine we did all the settings. As you can see, there is no IEC anymore on the display because the device timed out. It automatically after some time switches back to its normal operation, because in the IEC mode the battery is drained a lot more than in the normal operation. During normal operation with display on, it can last up to 10 years. With the IEC interface it would not be possible if the IEC would be always on. So let's say I don't know about it, I just didn't realize, and I click on Save Config to Device button. What will happen? The device tries to save the values. However, it fails to do so. So a GIF is shown so that I know what to do. So I will just follow what I've seen on the picture, and here we go. And the configuration is saved. Okay, so this is the pulse counter mode. I will switch to signal tester mode, where there is the same settings and there is this extra setting. So I will now switch, for example, to periodic, and again save. So now I'm changing the mode of the device. When you are changing the mode of the device is reinitialized. So you see again the starting and the release number. And in this signal tester mode, it's quite interesting mode for evaluation of the IoT network, for example. and of coverage of narrowband IoT. You can either set it to periodic, manual, or manual plus periodic. I will explain what it means. Here is the period with which the periodic messages are sent. So currently it is 900 seconds, which is 15 minutes. And this is the length of the payload. 512 bytes. You can reduce it if you want to do some economy with the data consumption. And that's it. That's what the device will do. It will send periodically the data, and on the display you can see the signal level, and you can see also the battery level, which is represented with these 3 dots. 3 dots means a full battery, and then it goes low and lower. There are also 2 dots on the right side which are not visible currently, and if you can see 1 dot on the right side, it means that the device got an answer, and if you see 2 dots on the right side, it means that the device got an answer from a remote server, and this answer was received under 2 seconds, which means that there is a quite good latency for a narrowband IoT network, because what we encounter in practice is more than 2 seconds for latency. So it kind of shows what is the round trip time, how fast is the connection. Yeah, so one thing is the signal, second thing is latency, and on the left bottom side you can see the remaining battery level. Okay, so what is the manual mode? Manual mode means that the sending is triggered by approaching a magnet to the side of the device. So I will switch to that mode. You can see that I just approached the head and it directly jumped into the IAC mode. So I will switch to manual, which means that nothing is sent periodically, and the device only sends a message when you approach the magnet to the side of it. Yeah, and as I didn't change the mode of operation of the device, like the global mode, whether it is signal tester or pulse counter, the device doesn't reinitialize, but it remains in the IAC in the IAC mode in case I want to do further configuration, which I don't want to do. So we just wait a bit for the timeout. I can, for example, remove the head if I want, and the device should then continue a normal operation. So let's wait for a bit. Okay, now it is checking the SIM card and reconnecting to the network, and now it will simply wait for me to approach the magnet. So I will approach the magnet, and it is sending a message. Yeah, so you can maybe also use it as a magnetic contact for detection of something, but this is not like the main purpose of it. It sent the message, it updated the signal value, and it is still showing the battery status. Now let's imagine I want to reconfigure the device, and I will show you how we solve the problem of having just one read switch to have 2 functions. Yeah, so I will approach the head, and I will need to wait a little bit longer. So you should see IEC in 3, 2, 1, 0, and it switches to IEC, and here we go. We can do the configuration, and we can change the mode to anything else we want. Yeah, so let's say I will switch it to I don't know, back to pulse counter if I want. I can do so. So yeah, I will put here the correct port and save, and we saved it. Okay, maybe you would ask, okay, you are sending some messages to narrowband IoT. What is the format of it? I will receive the UDP frame. I don't want to reverse engineer it. I want to know what is the content. So, in case you want to know that, well, this is the URL at which the configuration graphical user interface is currently available. It's ACRIOS-X.blade.acrios.com. It will be later moved to GUI ACRIOS.com with some initial menu where you will select whether you want to work with ACRIOS converter or ACRIOS-X, but currently it is at this URL. At this URL, which is viking.acrios.com/quickstart, and then you go to pulse counter with display to NB-IoT integration manual. There is a description of, I would say, everything you would need to know about this device. So there is things like what is a pulse output, counter integration. There is a list of commands which can be uplink commands. So these are different messages which can be received from the device. On newer devices, this is used, ACEX, which is a periodic report of measured data with Coulomb counter, which means that it also reports how many milliamperes were accurately consumed from the battery, so you can really have the power consumption under control in your application. You can go in detail through this or contact our support if you need any further explanation, but there is a full list. Here is a list of commands which you can send in ASCII to the device to modify any configuration which is modified from the GUI. You can also modify it using narrowband IoT, and you can also remotely reset the device. You can remotely read the archive, and you can clear the archive remotely, etc. And you can see there is also some settings for LWM2M, but it is currently under development and not available. This is the model of a single pulse input, so you can see how it looks like. There is some limitation for the maximum frequency of the input signal, and the information about device management, how it works, how the IEC protocol communicates with the device to read the archive, how it works in the programming mode, and the list of registers which is available in the programming mode. So this means that you can also, the same settings you can do via UDP, you can do also via IEC interface, and you will later be able to do it also via the LWM2M. Okay, so here is everything is explained here. So it is being improved continuously, but it already contains a lot of information. So here, for example, is the section of the data as it is received, and an explanation what each byte means, and so you can understand. Okay, I think I've shown and frequently asked questions. Yeah, so this is I think the most important part of this document. You can go through it yourself if you want, if you need documentation of the messages, for example. And now there is a little extra. Well, I will also show how you read the archive, which is important. So let's try to read the archive, which will read the sample data out of the device. So I will approach the IEC, put it here, and I can click read archive. So we should see the archive have been read here, and the value is 0. This is the OBIS code, this is the unit, and this is the time and date. Yeah, so you can see that we are playing with the device. Yeah, to be honest, this is my second trial to record this video, because on the first trial I got a phone call, so there is some history here, but we still are keeping the counter value at 0, so we have 0 here, and we are switching the mode from one to other, so we are starting again and again, so you don't see any periodicity at these timestamps, but yeah, maybe here is some periodicity. Okay, and we can also change the counter value, so In case we want to put there, for example, this, we can do so, and now the value is set. We can remove the head, and if we wait enough, we should see the 1, 2, 3, 4 on the display being shown. You can switch the interface to different languages, currently English, German, which should be reviewed from linguistic point of view, and also Czech is available. Here you can download the drivers for the IEC interface. If you order this head from us, this head is not part of the packaging, so just be aware that if you don't have any IEC head, or if you want the head which we used during the development, you can order this head from ACRIOS as well, separately. And you just need one head for as many devices as you want. And also an important link is this link in black, which actually goes to this page. Yeah, so where you can find definitions of all the payloads. Okay, yeah, and the device timed out from the IEC, and you can see 1, 2, 3, 4 being displayed on the display. So I mentioned a little extra which I'd like to show you. Currently the firmware update via IEC interface is not supported in this GUI, but we have some early support which is available using a Python script. What we can do now, we can execute a firmware update of this device from a local file which I have here. This is a file containing a new firmware. This is the CRC of the firmware, which is checked at the end of the firmware update, and now I will perform it. So I remove the cover, I remove the battery, and what I will do now, as you can see, for changing the battery it is quite good. You can remove the battery, and I guarantee you that this device using the supercapacitor will run like this at least for 1 week. Yeah, so if you need some time to change the battery after 10 years of operation, so well, there is no point in changing the battery, because well, in 10 years we don't know what will be what will be the technology. If NB-IoT will still be the technology which is widespread and used, but well, in case you need to change the battery, you can do so, and the device will not stop its operation. But I want it to stop its operation, so I will force it. I will short circuit this connection here using, at least I used the screwdriver. And what I will do now, I will start the firmware update by hitting enter in this window, and then I will quickly connect the battery and put there this, because I only have several seconds for the serial bootloader. Further, when this is supported in the GUI, there is a command, IEC register, which resets the device, so you don't need to do this in such a tedious way. Okay, so first I hit enter here, and I connect, and I put it here, and it is being uploaded. Okay. Now we wait for the upload to be done. If I remove the head now, the device is without firmware, but it still remains in the bootloader, and you can repeat the process as many times as you want. So well, I can try it now. For example, if I break it, yeah, so you can see that it's still blinking, waiting for the data to be received, and yeah, it failed. Oh, so I will repeat the firmware update process. So you can see it's really robust, and now it should start again. Okay, so I will reset it, and it will start again. Yeah, sorry, I didn't follow the steps. And we are back. So now we can wait for the update to happen. And after it's done, we will see the device load and start the firmware. The speed of the interface is 9600 baud, so it takes some time for the firmware update to happen. So this is not the recommended way of how to update the device. NB-IoT is faster in this case, but it is good always to have a backup in case there would be any update in the future, and you would find yourself with a device with older firmware, which, for example, doesn't include support for your country or anything. So it is always good to have a local backup for the firmware update. Talking about local backup, some customers don't like to have a web-based interface. Well, I will let this run on the right side of the screen, and on the left side I will put there the GUI. There is a little button here, install ACRIOS GUI. If I hit it on Windows and Mac, what it will do, it will install this this whole web-based GUI to run locally. So you will basically find yourself with an icon on your desktop, and you can click the icon, and it works the same way as if it was run from the web. So in case you would be afraid of, oh, they give me this web-based GUI, but when I am somewhere in a shaft and I want to install the device and I don't have internet connection, well, don't worry. You can, before going to the installation site, you can install this GUI locally and then run it from local installation. Okay, so the update is being done. Let's wait for a couple of minutes. Also, please contact us if your application requires ATEX certification, because currently we are in the process of gathering requests for ATEX certifications for this device, because there is a lot of use cases already even without the ATEX certifications. So we start with this, and later we plan to have ATEX certification for the device. But it is designed in a way that the certification should be doable, should be feasible. Okay, so now the CRC, and CRC is okay, and we are booting, and the device will boot. And starting release 112, and you can see from the name of the file that it is 112 release. So that would be from me. Thank you for watching, and see you next time.